So, page 46, we'll be talking about moving from one graph to another. Okay, it's actually the bottom of page 46. So it says figure 217, which I have given you a copy of, but it's incomplete. I would like to go through it with you and just sort of draw them and explain a few things. Figure 217 summarizes all the possible dt motions with their corresponding vt graphs and acceleration values. We can use the graph segments shown here to create vt graph sketches from the dt graphs and vice versa. So let's just spend a few minutes talking about this particular series of graphs. So the first column shows the dt graph, and the second column shows the vt graph. So when the vt graph is flat right at 0, well then obviously your velocity is equal to 0, right? And because the vt graph is flat, then that tells us the acceleration is also 0. And the example, we're going to be using track and field here. Track, I guess, only. The example is a person standing ready at the start line. Yeah. No.
No, you can't. Not good enough.
Looks like a dog. See? I like doing this. It's fun. Okay. Now, constant velocity. You'll notice here, and we should probably put on here that we should probably put a 0 right there. Now, you'll notice that the dt graph is positive. It's above. So, in fact, this person is actually starting somewhere that's to the right of the origin. It's, in fact, not starting at the starting line, right? Most people would assume that the start line of a race would be the origin, right? So, in fact, the example should probably have like a line there indicating that they are to the right of the start line.
Wow. It's like a relay.
I suppose. Good idea. Right? Does everybody understand why? Because the position time graph here is above 0. So in other words, they're not starting at the origin. It is kind of stupid, but
it's like the 200 is a 800 meter.
Sure. Sure. Okay. Now, under stopped as well, you'll also notice that the next one here stop is exactly the same. The only difference is that the dt graph is below. The vt graph is still right on 0, meaning that the velocity is 0, the acceleration is 0. Now, does the monkey have to be facing the other direction? No. Well, this just means that they are starting at a negative spot. They're behind the start line. So, in my mind, all it really means is this.
Yeah, it must be nice to be able to do that.
It is. It's very nice. Oh, I lost his head. Okay, so the way I read it, I'm reading, I'm reading it like this. Does that make sense to you? If you want to write it the same as in the book, that's fine. But to me, it just means that they are to the left of the starting line. Does that make more sense? Stefan, would you? Yeah? That's my interpretation of it, right? Because if you're stopped, you can't tell which direction you are going because you're not going or going to go. All right. Constant velocity. Now, constant velocity is shown on a dt graph by a straight line, right? Straight line. You'll notice the velocity time graph is also flat here, but just not at 0, right? Okay, so in this one, particular one here, they've got velocity is greater than 0. In other words, it's positive. The acceleration is the slope of the VT graph, but in this case, it is still equal to 0. So in our track example, what we're talking about is someone running at a constant speed.
How do you draw a guy running at a constant speed? It's one picture. How do you know that?
Good point.
What's running there?
Oh, it's much more fun to draw stick people running. Running at a constant speed.
Big drawing.
Thank you. I've done this for several semesters, so. All right, so the second constant velocity one, you will notice it is, the dt graph is straight. That tells us that it's a constant velocity, right? But in this case here, the vt graph is below 0, so it's, the slope of this is negative, right? Negative slope. This means that our velocity is less than 0. And our acceleration is still 0. So in fact, what you've got here is you've got a stick figure running in the opposite direction. Now we know that it's the opposite direction here because, right, well, because it's negative, right? And it's moving. Oh, and then I got to flip.
Cat.
That doesn't help you with getting examples.
Yeah.
All right. So we've got our stick figure running at a constant speed in the opposite direction. Now, speeding up, the dt graph shows a curve, right? You'll notice here that the velocity time graph is now increasing at a constant rate. It's above, so our velocity is greater than 0. Our acceleration has a slope, so it is also greater than 0 because of positive slope here, right? Mary, you're watching? Positive slope. Positive slope, which means that our person is doing what? Speeding up. And you can see the picture there. Oh, yeah, I can.
A little arrow behind him, the big arrow in front of him.
Yeah. How's that? Okay, it's one of my better ones.
It's not bad.
Obviously, the next one here, it's curved down, so we are running to the left. Our velocity starts at 0 and becomes more and more negative, so we are in fact speeding up to the left. Our velocity here is less than 0, it's negative, moving to the left. Our acceleration is also less than 0. So here you've got a negative acceleration, but because the velocity is also negative, it means it's actually speeding up to the left. Speeding up to the left. And so basically our person is, oh, he lost his arms. Speeding up to the left and running with no arms.
How from the, I don't know the evolution, we can't just say that. Everything else makes sense to me.
Slowing down. The slope here goes from steep to 0, right? Which means the velocity time graph goes from some positive value down to 0. So in this case here, my velocity is bigger than 0 because it's above, but my slope of my velocity time graph is negative, and so that means my acceleration is less than 0. When the signs are opposite, the velocity and the acceleration are opposite, then what does that mean? Slowing down. And so you can see here, just like in the picture, the runner is realized that she's won the race, and she's raising her arms in celebration and slowing down. And one arm appears to be longer than the other. So the last one, very similar, slowing down. The slope goes from steep to 0. So my velocity time graph goes from negative to 0. So the velocity here is positive or negative, Zach? Negative, because it's below. But my acceleration, which is based on my slope, Mary, would be positive. So because the signs are opposite, it means they are slowing down, but simply in the opposite direction. Oh. Right? So what this means is, if you'll look on the next page, on page 48, how do you construct a VT graph from a DT graph? Now we've done ones in grade 11, we've done a little bit of this, we're going to expand on that idea a little bit, and we're going to go the opposite direction, which can be quite challenging, so pay very close attention. Page 48 says, to construct the VT graph under the DT graph. Now I didn't put this on a handout for you guys, but it's there. Break the DT graph into distinct motion sections, extend the times down to the VT graph. Calculate the slope at the start and end of each DT graph section. So we're going from DT to VT. So we're going to find slope, mark the value or estimate of the slope of the VT graph. If the slopes are equal, then that means it's constant velocity, and it looks like that, it's flat. If the slopes are not equal, then you have to ask, is the second slope greater than the first? And if that's the case, then it's going to be speeding up, and it looks like that. And if it's not, then it's slowing down, and it looks like that. There's no doubt in my mind that constructing a DT graph to a VT graph is the easier of the two. So let's start with that one. Now, do you guys have this handout? This is now on page 49. It's on the back side? Excellent. Okay, so they show the steps there in the book if you want to follow along at home or something like that. Well, let's just sort of do it together here. So we've got position time graph on top. We have velocity time graph on the bottom. So remember, the velocity time graph is the slope. So what's the slope right here? It's some positive value, right? Some positive value, and right here it's obviously 0. So we're going from a positive slope to a value of 0. So I graph a positive slope right there, right? My slope of this is equal to the value here, and clearly the slope approaches 0. So the slope approaches 0. Now it should be right at 0 at that same point right there, right? Should be right underneath it. The time is the same, so to speak. What's the slope for this entire section? 0. So I graph a value of 0. Here the slope goes from 0 to some negative value, right? Some negative value right here. We don't know how much. But we do know that eventually it appears to, like it curves here, and then it appears to do what? Straighten out and become constant slope. So I'm going to go from 0 down to some negative value, and eventually I'm going to flatten that out because it becomes constant.
I see.
Look at the position time graph.
This is the position time graph here.
Yeah.
Okay?
It's going up, but there's no other numbers or anything, so how do you say it's going to 0? It's going to.
Oh, like right here?
So it's going to.
It's becoming flat, although you can see here it sort of goes from like not, like there's some slope to it and then it becomes instantly flat, right? This probably isn't a very accurate one. It should probably be more, curved right into 0. This one appears to jump to 0. In fact, it should probably look something like this. It should probably go like this and then go straight down to 0.
Where?
Because it doesn't go smoothly from some value to 0. It sort of jumps to 0, doesn't it? But once again, the art department didn't meet up with the physics department and the textbook people. Okay, so at your skill level, relatively simple, I'm hoping. However, flip the page. Here's where things start to get your brain working. Okay? So on page 50 now. Page 50 talks about the opposite thing. Now we're going from velocity time to displacement time. So you got to reverse your thinking. You're taking a graph of the slope and making the DT graph from that. Okay, so the flowchart says to construct the DT graph under the VT graph, break the VT graph into distinct motion sections, extend the times down, same as before, allocate positive or negative to each area on the VT graph, mark the value or estimate of the area on the VT graph. Is the VT section horizontal? If a velocity time graph is horizontal, Jory, that means constant velocity, and so your DT graph is going to have to be straight, right? Up or down, like you can see there on page 50. If the VT graph is not horizontal, then that means we have some type of acceleration. And then you have to determine, is it speeding up? And if it is, then it curves up or curves down. And if it's not speeding up, it's slowing down, then it's flattening off or flattening off, either way. This is all figure 2.20, the flow chart that I'm looking at. Do I need to go through the flow chart one more time?
Yeah.
Okay, follow along, you guys. You guys can't be taking little mini breaks. Listen, okay? So we're going to go down to the diamond there where it says, is the VT section horizontal? If the velocity time graph is horizontal, then that means that the velocity is constant, which means that the DT graph is either up to the right or down to the left. Or down to the right, yeah, right. Up to the right or down to the right. If the VT section is not horizontal, then we have acceleration, and then you have to ask, is it speeding up? And if it is, then that means that it curves up or curves down, but getting steeper. If it's not speeding up, then clearly it must be slowing down, which means it has to curve, but it has to get flatter or flatter, one way or the other. Yes? Flatter or flatter. Okay, so let's try one. Pay very close attention. Here's our VT graph. We're going to break it into sections. I'm going to go like from there to there, from there to there, from there to there, from there to there, and there to there, and there to there. Right? We're going to break it into sections. Okay, so now what does the flowchart say to do? Mark the value or estimate of the area in the graph. So we're going to have to see whether it's positive or negative. Oh, thank you. Okay. We're going to have to say whether it's positive or negative. So here we've got velocity, which is negative. Here we have velocity, which is positive. Here we have velocity that is constant, right? In fact, maybe we should be marking that, right? This is negative, and this is negative and actually going towards 0, isn't it? Right? How am I going to mark going to 0? And it's coming from negative to 0, right? How about I mark it like this? How about I go arrow towards 0? This one is positive and going away from 0. So we would probably mark that like, do I want positive? Do I want arrow going up? Okay. Here it's constant. Whoops. Constant positive. Here it's actually still positive, but going towards 0. Here it's in fact 0, and it's marked right on there, right? The velocity is 0. And here the velocity is negative and moving away from 0. Okay, so how do we draw the graph? Well, these points here have to be sort of marked off down there. Okay, and in fact, that's what they've done here, right? Actually, they've done, I didn't really need to do both, did I? So marked off there and there, 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 there. Actually, you would probably, because you haven't drawn it, you would mark them on the axis, right? You'd mark them on the axis. Okay. Okay, so here's the hard part. How do we draw? The velocity time is negative, high negative, and going towards 0. So at this point right here, the slope has to be negative and approaching flatness, which is just 0. So I'm going to draw it like this. Right? It goes from very negative to 0. Very negative, so steep, and approaching 0. Why is it below?
Slowing down in negative.
Slowing down. I'm going to the left, and I'm slowing down. Right? Negative velocity going to the left, approaching 0 means slowing down. Jordan.
So why would it go down first? Aren't you starting at a constant speed and then slowing down?
But it's negative.
It's negative velocity.
That's
Right? Yeah, this is the position now. You can only assume that where you start is the origin. Did you want to start somewhere besides the 0?
It would just make more sense if you started below it because you're slowing down and approaching.
You're not approaching position 0, you're approaching a speed of 0. Right? It's the backwards thinking. Right? Shift into reverse. Yes, I know you don't. Okay. So now we've got a value of 0, which means my slope here has to be 0. Value of 0 means slope of 0. This is the value. We're looking at the value here, and we're drawing the slope, right? Right? Okay. So value of 0 going to a value of positive, right? Which equates to a value of positive equates to a steep slope. So I go from 0 to a steep slope. Now, why does it only go to there? Well, that's true, but why does it not go back to a displacement of 0? Well, the only way really to tell would be to, and I don't know if you can see in yours, but can you see, does this area equal this area? The one on the left is a little bit greater, which means it doesn't have a total displacement of 0, which means it has to stop right there. Now that's definitely tricky. You just some random spot just below. That's all. Yeah. Well, no. I guess technically, Quinn, you could find the area, the negative area here. Let's say it's, well, maybe we can figure it out, can we? It looks like, shall we say it's 2? Like it's 2 over and 2 down. 2 times 2 is 4. Half of that is 2, right? So in fact, this should be a displacement of -2, right? And then the next one looks like 1.5 times 2 would be plus 1.5, right? So in other words, this point right here should be at negative 0.5, should it not? Yeah? Now, I'm not going to get into that too much. I wouldn't worry too much about that. I might ask you a single question about that, but I certainly wouldn't make it a big problem. Okay, so now here we have constant velocity. How do we show constant velocity on a DT graph? Straight line. Now, the textbook people have screwed up here. Can you tell me what they've screwed up? Right here. Look at this spot right here and right here. What have they screwed up? Look at the slope here and the slope here. It's, what do we mean by it's off? What should it be, Annie? You're on the right track. Should it be steeper or flatter? It should be flatter?
No, it should be the same.
It should be the same as this, right? Because what's the value right here? Like, let's say the value goes like 1, 2, 3, 4, right? The value here, like it goes up to say 4, and then it stays at 4. The slope has actually gotten slightly less, hasn't it? This slope should actually be, it should be more like that. It should be as steep. It should be the same steepness as it is right there. Shouldn't it? Yeah? Okay. So having said that, if you ever work for a textbook company, make sure stuff like that doesn't happen. Because it's wrong. Okay, so constant speed is shown by the straight line. Okay, now here the velocity goes from that positive value down to 0. So what does it do? It flattens off. Okay, and I'm not going to worry too much about position here. I'm more interested in the shape. The shape is what we're getting at, right? So we're going from positive velocity, right? Positive slope down to 0. 0 slope is shown as flat. The velocity time graph here is 0. The velocity is 0. How do we show velocity 0 on a displacement time graph? Flat. So flat line. If we actually figured out the displacement, we could actually figure out what the height should be, couldn't we? We could. Here, the velocity time graph goes from 0 to some negative value. So it goes from 0, in other words, flat, down to some negative steepness, right? And this one is not as far down as this one, so it shouldn't be quite as steep as this one. Could we figure out what that spot should be? Yeah, we'd have to figure out the individual displacements, and it would tell us that it's overall positive. Not an easy task. Am I right? Yes, I am. Yes, I am. Okay. You now have, there's some assignment there on page 71, 22 to 28. What I've done is, because the graphs, clearly you need to draw on the graphs, and so they've provided me with some handouts to go with that. So I will do that, and I will also tell you that the back page of this is a hand-in. Okay, so I encourage you to work on these. This is hand-in that will be in, I'll say, like, I don't know,
Just the back side,
just the second page.
let's just do that.
Can we say Wednesday? I'm not gonna help you with the handout, I'll gladly help you with this one. Spend some time practicing, Zach. Don't just play the game.